Welcome to May 3rd's LeetCode Challenge, shortest unsorted continuous subarray. Given an integer array nums, you need to find one continuous subarray that if you only sort the subarray in ascending order, then the whole subarray will be sorted in ascending order. Return the shortest such subarray and its output is length. So basically you want to find the shortest subarray, but you only need to return the length of it. So we're given this integer array nums here, and then we want to basically find the smallest continuous subarray where we sort that. So the smallest subarray size would be 5, and if you take if you take the index 1, which is 6, 4, 8, 10, and 9, and you sort that in ascending order, then the whole entire subarray itself will be in ascending order. This one is already sorted, so therefore you don't need to sort it. So you don't need this. The subarray is 0, size 0. If the subarray contains one element, then obviously you can't sort one element, so therefore the size is 0 as well. Our constraint is between the length of nums is between 1 to 10 to the 4, and each index of nums at element I is between negative 10 to the 5 to 10 to the 5. Can you solve it? And the follow-up question is, can you solve it in big O linear time complexity? So linear time complexity, yes, we could probably solve this using linear time complexity using a stack. So let's say if we were to sort it, and then we use a stack to sort it. So we use a stack to keep track of the first inconsistency and follow the lower and upper bounds as well. That's kind of cool. So basically we're going to have we're going to make a stack to store it. So first thing we need to do is have a lower bound and upper bound. So compare the elements at the same index of the both lists. So we make two lists, I guess. And then once you encounter a mismatch, or there's an inconsistency, therefore we're going to use that to find the upper and lower bounds of the unsorted array. So we're calling something called lower, upper, and then the lower bound is going to be the length of nums minus 1. And upper is going to be 0. So we're going to have a stack, and that's going to be an empty list. And we're going to loop through length of nums as well. So for index I in the range of length of nums, what we're going to do is, while stack exists and nums at index stack from the last member is greater than nums at index I, So while stack exists and the last element is greater than the element index I, what we're going to do is we have to update the lower bound, and we update the lower bound with the minimum between those two. So the minimum between the lower bound we have and the stack, last element of the stack, stack.pop. And then once we make the loop, we could basically append I to the stack. So what we just, and then we define another stack here, so we do a double pass. So what we did here so far was that we defined a lower bound, upper bound, and then we defined a stack as well, being an empty list. We loop through each element in each index in length of nums. Well, the stack exists, and the last element, the last index, is greater than nums at index I for each element here. Then what we're going to do is find what the lower bound is, what the lowest number we could of the subarray we could affix to, and then we basically update with the minimum between lower and the last from the minimum between the lower we have count so far, which is the last element, or the last element added to the stack. Once we exit, we just add that index I to the stack. So we're going to do a similar approach. Now, this time we're going to find the upper bound. And the upper bound is going to be the max between the upper and the stack.pop as well. So, because we've defined a new stack here, we just do basically the same code for I in the range of length of nums while stack exists, and nums at the last element of stack is less than nums at index I. This time we're going to find the upper bound. So upper will be the max between the current upper we have and stack.pop. However, what do we pop from the stack? We have to pop the last element of index I added before. Alright, now that we have an upper and lower bound, return. Basically, we want to return the length between the lower bound and the upper bound, right? So that will be return 0 if the lower bound is greater or equal to the upper bound, meaning that there's nothing, we didn't find a lower and upper bound, such as in this case or this case, example 2 and example 3. Else, return the length. So that'll be the upper bound minus the lower bound minus index of plus 1, right? Because keep in mind that 0 is included in as well. Alright, run the code. Let me see what the issue is. So we're a little bit one off here. Alright, we have lower, upper, minus 1, 0. Let's put a space here for I in the range of nums. Will the stack exist? It's greater than nums. Lower. We're going backwards this time. So instead of I have to loop in the opposite direction, so it'll be length of nums minus 1, going in reverse direction, and decrement by 1 each time. Let's see. While stack exists, stack of -1 is less than. This is what I got wrong here. Alright, submit. Alright, there you go. So this, so time complexity is big O of n. It's actually big O of 2n because we do a for loop twice, so big O of n, I should say. And space complexity is that we use a stack twice as well, so big O of n again. Alright, that's it. Have a great day, guys.